Hey, good morning, students. This is Unit 2, Day 1, March 25th. We're talking about Earth's layers. We've got a couple different learning goals today. First one is we're going to learn a little bit about waves. We need to do this so that we understand earthquake waves, stuff like that. We're going to talk about how they bend when they get to different materials, how they can travel through some different materials at different speeds. And then that's going to allow us to start to investigate the interior of the Earth, look at the different layers underneath the crust. We're going to specifically then start talking about earthquake waves, seismic waves, and we're going to review how pressure and temperature are also going to affect the interior of the Earth and link those two things together to the point where you guys can describe and label the different Earth's layers. So getting started, I want you guys to imagine there's a field of grass merged into a field of quicksand. And the first question is, which one do you run faster on? And the obvious answer is grass. So over here, we have what's called a fast medium. Medium means the substance that the wave is traveling through. And in this case, we're pretending we're running on it, but that's going to be us representing the wave. This is all a metaphor, an analogy. Okay, so when they get to the quicksand, they're going to slow down a ton. Now, these three people are running side by side. They're all the same speed. Question is, who slows down first? The top, middle, or bottom one? And the answer is, well, yeah, the top one's going to get to this layer first. They're going to slow down. The other two are going to keep going. So if you're looking at it, let's see, which way, here we go. Oh yeah, for going across, what's going to happen is the top one is going to get stuck and it's going to end up pivoting upward. So, ooh, that was all backwards for me. Okay, so there they go. They're going along. Top one gets stuck, has to slow down. The other two continue at a higher speed for quite a while. They slow down only later. And what it does is it staggers and offsets the wavefront, the direction the wave is traveling as well. And so when waves get to materials that change the speed, different medium, then they also cause a direction change of the wave. And this is called refraction. What I just did is I drew in wavefronts. So those red lines now represent the direction the wave looks like it's lined up across. And the green arrows represent a ray, the direction the wave is headed. So you can think of the green arrows as like a velocity vector, and the red arrows are how the wave is lined up. And you can see that the way the wave is lined up changes after it gets to the new medium. So I want you guys to use this analogy. Let's do it one more time here. So we've got three people running straight towards the new surface. Figure out which one is going to either get to speed up first or slow down first. In this case, we're going from a fast to slow medium, so they're going to slow down first. At that point, take your fingers along those three lines, figure out which one gets stuck, hold that one in place, and see which way your hand pivots to understand which way something is going to refract. This is a great analogy to be able to think things through. And again, vocab words, medium means the substance the wave is traveling through. Refraction means a direction change because of a change in medium for a wave. So they're going along, top one gets stuck, wave pivots upward, and you can see that in either a ray model, which are the green lines, or a wavefront model, which are the red lines. Okay, cool. Let's go look at some examples of this. So first up, waves in the ocean could be going any which direction, but as they move towards shallower and shallower, basically move in towards the beach, the shallower depth is causing the waves to slow down. It represents a change in medium, even though the wave is still passing through water. It's having to travel slower because of the way it's getting shallower there, and they will end up oriented towards the beach. You guys may have also seen a mirage. That's where a hot air layer is causing refraction. You've probably seen rainbows, maybe even a double rainbow. And that's where the water droplets, the transition from air to water, is causing refraction. And you've definitely all seen lenses, like in people's glasses or contact lenses or telescopes, microscopes, whatever. That's where a air to glass medium change causes refraction. So we can refract water, we can refract light, we can refract whatever. It doesn't matter what kind of wave it is, and that's something we'll talk about more when we get to the waves unit. Here are some more examples. Here's a ray model. Ray comes in, the air is fast, that's like grass. The glass is slow, that's like quicksand. So if we had a person here, here, and here, if we had three people running along, who would get stuck first? The answer is the one on the bottom would get stuck, the one on the top would keep going, and that would pivot it around the corner, just like you see here, it causes a bend in the direction. When the wave changes direction because of a medium change, again, that's called refraction. So you can see that happening with light through glass. You can also see it happening with water. If we're here in class today, we would definitely do this hands-on. All right, Second thing we need to know about is two different types of waves. One of them is called longitudinal, and I wish I had a slinky today, or again at school. But if you were pushing and pulling the slinky, you could get compressions and then also expanded out sections. And this is called a longitudinal wave because the direction that you're pushing and the direction that the wave is moving match up. They're the same, they're parallel. So I think of L's as being the symbol for parallel, longitudinal waves, parallel. What would perpendicular be? A T, right? So here, if you shake the slinky up and down, the wave still goes that way, but those two things are perpendicular. So you're moving up and down, but the wave travels left to right in both cases. So perpendicular goes with transverse, parallel motion goes with longitudinal. Just imagine both of those ways to shake the slinky. There are two different ways to orient a wave, where the disturbance is parallel to the motion of the wave and where the disturbance is perpendicular to the motion of the wave. So which kind of wave would that be? Oh, that's transverse, right? All right. By the way, longitudinal waves are also sometimes called compressional waves. Any sound waves getting to your ear from your speaker are this type, where the air gets squished and then expanded, squished and expanded. You can think of a bass speaker as like pushing air and making pulses of high pressure and low pressure, which is what sound waves are. Okay, cool. So let's keep going. Why do we care about this? Well, because you can do both of those things to the Earth. If there's an earthquake, you can get both kinds of waves. Now, which one is transverse? Hopefully you picked the S wave, the one on the left. It's getting shaken up and down even as the wave moves left to right. That means that the P wave is longitudinal. The way that it's getting compressed and expanded runs parallel to the direction the wave is headed. Okay, second idea. P waves are called primary waves. S waves are called secondary waves. Based on that nomenclature, that naming system, which wave do you think is faster and gets to the seismic detection place first? And the answer is P waves. Primary means they get there first. They must be traveling faster. S waves are secondary. They get there slower. Now, one other weird thing. The S waves can only go through solid medium, whereas the P waves can go through solid or liquid medium. So that's one other key distinction, and we'll review that in a little bit. All right, so let's keep going here. First up, these are just recordings from 3 different earthquake monitoring stations, 3 different seismic sensors. Which seismic sensor, A, B, or C, was closest to the epicenter, the place where the earthquake originated from? And this is just a graph of waves over time. And the answer is it's going to be the one that took the least time to get there. Waves travel with a certain speed, and so if they're covering a distance, it takes time. The less time, the less distance the wave that they covered. Station A is closer to the earthquake than station B and C were. So using time versus wave graphs, time versus amplitude, you can actually check where the earthquake was, and you can triangulate this if you want to. You can figure out the exact location of the earthquake by using at least 3 recording stations. Okay, second question. Which set of squiggles are the P waves? The little ones or the big ones? And the answer was, well, P is primary. They're the ones that get there first because they travel with a higher speed. So P waves are going to be the first ones to get there. S waves, which stands for secondary waves, are going to be the second one to get there. Okay, so P wave, S wave. This station's closer, this station's farther, this station's really far. That's a little bit you can tell about just from like recording the earthquake waves. Okay, now before we keep going, let's actually tinker with the simulation here. Hold on. We're just going to do some quick phase change demos. I hope you guys remember the jar of marbles I had, shaking the marbles, demonstrating with a small amount of shaking that they acted like a solid, which is what we're seeing on the screen right now. With a larger amount of shaking, they'll start to swirl into a liquid. Let's shake them up a little more, add some thermal energy. Now they are generally stuck together, but the shape continues to change. They're spreading out to a new shape to fill the bottom of the container. We have now reached the liquid stage. Another thing we can do is we can shake them even more to the point where they expand to fill the entire container. Now they're acting much more independently. This is more like a gas, although they're still clumping a lot, which is still like a liquid. So let's heat it even a little more to get this to fully the gas stage where they're all just acting independently, bouncing off like crazy in a chaotic, disorganized kind of motion we associate with thermal energy. Okay, so there we go. We got a gas now. Now I hope you guys remember what would happen if I mashed my hand down into the jar of marbles. Are we getting more or less clumping now? We're gonna have to cool this off a little too. And what happened with the marbles was when I was able to mash my hand down hard enough, I forced them all to the bottom. Hopefully this doesn't explode on us. Oh, yep, there we go. Well, you guys can tinker with this later. Point being, we've got different ways to transition between solid, liquid, and gas. And I want to direct your attention over to the graph right here. You can change something's phase either by using temperature or by using pressure. So you guys may recall when I drank the boiling water. Example of that was we had water that was almost boiling. It was about 70 or 80 Celsius. Then I put it in a vacuum chamber, pumped out all the air, and you guys saw it go to a rapid boil. What we'd done was we'd had a liquid that was hot at high atmospheric pressure. When we dropped the pressure out, it was able to phase change to gas and go to a rapid boil, and you guys saw most of that water kind of spread out throughout the vacuum chamber. So I hope you guys remember we can phase change things with pressure or temperature. Important concept. Okay, so let's head back now to our slides. You can phase change things with pressure or temperature. You can make it a solid, liquid, or gas depending on how you cause those transitions. Both of those are important factors when we talk about the Earth's interior. Where would you guys expect the highest temperatures to be? On the inner core or the surface? And since we talked about the Earth as a heat engine with high temperature inside, low temperature outside, and heat flow generally from inside to out, hopefully you're getting that the inner core is going to be our hottest temperature. But on the other hand, where's the highest pressure? On the surface or down below a couple hundred miles of rock? And the answer is also going to be on the inner core. So those are actually conflicting factors. Higher temperature wants to make the rock melt into a liquid, but higher pressure also wants to solidify the rock back into a solid. Those two factors are fighting each other. And so at various points in the Earth, we have different stages of solid or liquid or plastic layer, as we mentioned one other time. And so how do we know this? Well, go back to the S waves and the P waves. One of them could go through liquid layers. The other one couldn't. They could both go through solid layers. So let's say we have our earthquake right here. We've got a whole bunch of places where we can record seismic data. The wave is going to travel around the surface. We're not worried about that one. We're worried about the different types of earthquake waves that'll go through the interior of the Earth all the way back to the other side here. First of all, which one is traveling faster, the red waves or the blue waves? And yeah, the red waves have covered a bigger distance in the same amount of time. So the red waves are definitely the faster ones. So are they primary or secondary? Don't look at the key. Don't look at the key. Okay, faster waves are primary waves. Slower waves are secondary waves. Okay, let's keep going. All right, hopefully you're noticing something right at this layer. The red waves kept going, the blue waves stopped. So remind me, which wave can't go through liquid layers? It's the S waves. And if that's the case, what you can tell is that this layer right here, which is the outer core, is liquid. So we know that the outer core is a liquid layer. What about the mantle? What about this layer here? Solid or liquid? The answer is solid-ish. It's kind of plastic layer. It can change shape a little bit, but it's effectively a solid. All right. Oh, here we go. We're going to jump partway to the end here. Okay. So hopefully that's the first thing you noticed. Well, things you noticed. Number one, the P waves are traveling faster than the S waves. Number two, the S waves cannot pass through liquid layers, so they stop at the outer core. That tells us that the outer core is liquid, but that the mantle and inner core is solid. Number three, hopefully the other thing you're noticing is there is some curving going on. These waves are gradually changing direction. Remind me the vocab word for waves that change direction due to a medium change. And hopefully you're thinking refraction. So these waves are refracting. That tells us a lot about the density, the thickness of these layers, and how it affects the wave speed. And we noticed in our earlier example that waves tend to bend towards the denser, slower layer. So you can tell that density is increasing as we go down, but that there are some sharp disconnects in wave speed. And so these distinctions between the mantle and outer core, they're not gradual. They happen pretty abruptly. Like it pretty abruptly goes from solid to liquid right at a line here. And you get these discontinuities. They have weird names like moho discontinuity and stuff like that. So this is how we know about the inside of the Earth, the interior. We have seismic data, which is earthquake waves passing through the Earth's core, and we can measure and listen to them in a bunch of different cases here. What's really cool is, let's switch to another application here. This is a link that I posted on Classroom. Oops. That's not what I want. There we go. I think you have to download this to run it. Nope. I think you can directly open it. Should be able to, oh, Flash Player. Come on. All right. Well, we will come back to this. I'll get this running a little bit later. Oh, I think you can also download it and open it from a zip file. There we go. Yep. So you can download and open that way. Okay. So P waves, it shows you the path of them. What I want you guys to notice is that there is a shadow zone right there. And if you follow the S waves, there's an even bigger shadow zone right there. Now the S wave shadow zone is a combination of refraction and the fact that the S waves don't pass through liquid layers. The P wave is strictly because of refraction, because of the way that the waves are curving. When they get to those medium changes, makes the waves not actually show up in this area right over here. There's also some surface waves. Those will travel right around the surface. By the way, this has been simplified a bunch. There are actually one kind of wave causing another kind of wave. You can get S waves through the inner core, and those can actually show up as P waves later on. So you can get waves changing types as they hit new layers. So the reality is a little bit more complicated in the example we're showing you. But an important idea to note is that we know that the mantle is solid-ish, the outer core is liquid, and the inner core is solid because of this information. We also have a good amount of data on wave speed, which can tell us about pressure and temperature as well. So this is basically how we know about the interior of the Earth. Alrighty. I think those are all the main ideas for today. I want you guys to start to learn the different layers for Earth layers. So we have inner core, outer core, that's pretty straightforward. Then we have the mantle, asthenosphere, and lithosphere. Lithosphere means crust and upper mantle. Asthenosphere is that plastic layer. Yep, so get those vocab down. You guys have an article to read. Let me pop that up real quick. The article, you can start about halfway down if you want to. Like you could start it right about here. There's some cool history and stuff. I mean, I thought this was interesting. But the part you need starts right here. You guys are going to go through, learn about each of these different layers, what it's made out of, like nickel iron or basalt or whatever, and learn about some temperatures, learn about depths. And that should cover it for today. There's a handout to go with this. You guys can print it if you are able to, or you can just do this on scratch paper and work off the handout. When you are done, then you should submit what you've got through Google Classroom to me, and I'll set that up as a quick follow-up assignment. All right, so real quick, let's review. There we go. Hopefully you understand something about refraction. When a wave gets to a different medium, a different material, it can speed up or slow down, and this can cause it to bend, change directions. You know that there are at least two kinds of seismic waves, two that we're going to be talking about. There's a bunch more as well. We're calling them S and P waves for secondary and primary. One passes through liquid layers, the other doesn't. They move at different wave speeds. They can refract when they get to different layers of Earths. You can use earthquake data to figure out what the Earth is made out of and identify those different layers. You know that pressure and temperature are kind of battling each other to determine whether each of Earth's layers is solid or liquid. For the inner core, which is solid, which one won? Temperature or pressure? And hopefully you're saying pressure. Pressure is the thing that's trying to make them solid. Increasing temperature is the thing that's trying to make them liquid, trying to melt the rock. And then hopefully by the time you finish that reading, you can label and describe Earth layers. All right, that's it for now. Thanks for tuning in.